cover the multi-head attention mechanism. And my assumption is that by now you have gone through the attention series labs that we had. You also have watched the course videos, or you have been part of the class and you're familiar with the contents. I highly recommend you to go through the series before watching this video in order to make this easier for you to grasp. Now, let's start. So multi-head attention, technically, it's similar to the attention mechanism, with one the main difference here is that in attention mechanism we process the the embeddings that we have at one go. However, in multi-head attention, instead of just doing the process one time, we break the process in multiple heads or multiple times. And the benefit of that is that we basically allow to each head, or you can think about each head as a separate model, each model to process the data separately, in parallel also. And that way, each head will be learning something new about the data. In compared to attention model that we just basically, like a vanilla attention that we just do using one head, and basically we learn everything at one go. So the main difference here is that when you're looking at the embeddings that you have, if we have, for example, K head that we are going to use, we break the embedding into K chunks, and basically each chunk goes to a different head, and different head basically performs an attention step. And at the end, we basically concatenate the result from each head into one basically vector. That is the dimension of that vector is going to be the same dimension that if you would have done basically just one attention over all of your data. And then we pass that to a linear projection, for example, in this lab for the downstream task. So what we do for the lab is that we start with building a simple multi-head attention. Then we're going to apply the multi-head attention into a sentiment analysis task. So let's just start. We had in the attention lab, we basically created already this scale dot product attention, which what it does again, we have a query key value. It basically calculates the dot product between query and key. It basically scaled that dot product by the square root of the size of the depth of the embedding vector that we have. If there is any masking, we basically apply the masking here. And again, remember, the reason we are applying just such a large negative number is that because after we have this masking, if we are doing a softmax, and if the value is really large and negative, the probability goes towards 0. So next step is that we apply softmax to the attention largest that we have. So now that gives us the attention weights. We dot product basically multiply that attention weights by the value matrices that we have, and that gives us the output. So this was the attention, basically attention, like a process, we can call it. Now, what we want to do, we want to implement the multi-head attention layer. So we started by creating a class multi-head attention, which it's a subclass from keras.layers. What we do here is that we're going to define as an input number of heads. That means how many heads we want to define for this multi-head attention. We also pass as an input the depth of the model, which is the depth of those embedding vectors that we have. And what we do here is that we divide the depth by the basically length of the number of heads that we have. Okay, we need to ensure that that's also the division basically doesn't have any left over. So that's also important to remember. Then what we do, we create basically WQ, WK, and WV, which are the weight matrices. And then we also have one dense layer that at the end gets the basically the data to basically combines or like something like combine all those attention heads that we have. Now we have a function called split head. What this function does is that it gets the X here, which is our input tensor. It basically reshape it first and it transpose it. So we just what we want to do is that if we have an input, we want to be sure that this input has a dimension of number of heads and the depth after after we divide it into multiple heads, and that value was calculated here. Then we have a function which is should call function. So this call function as an input gets 3 values: V, Q, K, and Q, and a mask basically in case you have a mask. So the first step is that we do a linear projection. We multiply our queries by the weights. We multiply key by the corresponding weights. We multiply values by corresponding weights. So now we have query key value matrices. Then we split this query key values, depending on into multiple chunks for different heads. Then we pass this basically chunks that we have for each head into our basically a scale dot product. And again, if there is a masking, we do that. So that gives us the scaled attention and attention weights. We basically transpose those scaled attention, and then we reshape those by concatenating those back into each other, because remember, each scale attention is basically scale attention is has basically multiple outputs from each head. So we want to concatenate those. So basically, this is what we do here, concatenation. And then we pass the final concatenation, which again is this value to a linear projection. So we pass that to a linear projection, and we return the output and attention weights. We return attention weights just for visualization here. So let's make one example. So here, basically, we create some dummy data, and we define that, okay, we are going to have 4 head as a multi-head. There's going to be 4 head. The depth of our basically data is 64, as we defined here. We pass that to our multi-head attention model. Basically, we do a forward pass. We're just saying that, hey, we want give us the output and give us the attention weight. So the attention weight looks like this, because we have 1 stands for 1 batch, 4 stands for we have 4 heads, and each head basically has a weight of, or basically attention weights of 10 by 10 as a matrix. So what we want to do, we want to visualize those attention weights, and this is what we get. So as you can see, think about, this is a dummy data, but think about an example that your query are basically 10 words, okay? So you have all these positions for queries from 0 to 10. And again, 0 to 10 here, because it's just each word with respect to every other word, including itself. So on head 1, as you can see, for example, location 1 attends maybe to itself more than the other ones. And as it goes, basically, the color grading basically here stands for the attention weights, like if it's higher or lower. But what's important here to notice is that when you compare head 1 to head 2 to head 3 to head 4, as you can see, the attention weights are different. What does that mean? That means each head has learned to for a given query to attend to a different position on the basically from the key value or key matrices or keys, depending on what basically it was important for that head to learn. So that's the whole idea of attention heads. So we, by having these multiple heads, we are going to learn multiple basically relationship or contextual learning, or contextual representation. So now what we're going to do is that we're going to use this as part of a sentiment analysis. So the simple way is that we also could use TF Keras layer multi-head attention. So multi-head attention as an input gets number of heads and key dimension, which is the same thing as we did before. So there's a data set that we're going to use, this spam data set collection. Remove that one. So this data set basically has SMS text, and it has labels as a spam or not a spam. So the first thing is that we do some text reprocessing. We do text vectorizations, and then we also need to, after we have this text vectorization, we need to basically be sure that we convert those to an embedding for our basically attention model. So we create a model. This model as an input gets the vocabulary size. This vocabulary size we defined here. It gets the embedding dimension that we are interested to basically learn. Sequence length is going to be what's the maximum length of any sentence that we want to basically process, and what's the number of heads that we are going to use. So we start by creating an input layer, and then we creating an embedding layer, which what embedding does basically, as I hope you're aware by now, is that basically creates this embedding like a contextual representation of word. I need to be really careful with what I'm saying here. So embedding, the contextual representation embedding is not contextual with respect to the sentence, it's with respect to the word itself, and word and other words, not within the sentence, for example, here. So we have then this multi-head attention layer, which we say we need this many heads, and this is the embedding dimension. As an input, basically gets X, which is the output of the embedding layer. So X is our key and X is our query at the same time. After that, we apply a dropout to the attention, basically output. And then we basically do some sort of like a layer normalization. And then we also add a residual connection. So we are doing these steps to basically follow, the paper for the transformers, for example. But overall, what you can see here is that the residual connection, the reason we add the residual connection is that to ensure that the information doesn't get lost, as we go through these different steps. Then we do global average pooling over the attention output. And then we have basically, if we are here, we are doing, for example, classification. So we will have a downstream task that we want to do. So we first apply some sort of fully connected layer. We add some dropout, and we do another output layer, which is also fully connected. We had one node because we are doing a binary classification with the activation of sigmoid. We basically create our model, and we say that the input of the model comes from the input layer and the outputs of the model come from the output layer. So here we basically initiate 4 heads. We create a model by calling to the function that we have. We compile the model with the Adam optimizer, binary cross entropy loss, and the metric we care here is accuracy. We basically vectorize our data. We pass the data to the model, and we let the model run. Here, I just ran the model for 5 epoch, and we get basically the test accuracy here was 100%. I think this data set probably is much easier than what we expect for learning. And then we basically pass some random text to the model to see if the model actually learns something or not. And the model predicts that, hey, this, for example, this is not an spam. Hey, can we reschedule our meeting to tomorrow? The prediction was not a spam. So this is a short summary of a multi-head attention. Again, the original instruction, or basically, if you read the paper, it's if you want to build the models that are more contextual aware or the more advanced, you basically need to have series of this multi-head, not just one multi-head attention. That means you need to have multi-layers, multi-head attentions, which we will cover in upcoming labs. Thank you.